Hello and welcome everyone. Thanks for tuning in to our freshwater stewardship community webinar. You'll just notice as you're coming in that your camera's off and your microphones are muted. That's just so that we can save as much bandwidth as possible. But if you have any questions throughout the presentation, feel free to drop them in the chat. And while we're waiting for a couple more people to join, feel free to drop in where you're tuning in from today. We love to see that, and we'll get started in just a moment here. All right, so it is 2 o'clock, so we'll get started. We're very excited to have our guest speaker, Liz, here with us today to learn about her work in paleolimnology. And we also have 2 staff members from Watersheds Canada. My name's Nicole Dubé. I'm the Freshwater Health Coordinator. And we also have Monica, who is the Communications and Fundraising Manager. So if you're having any tech issues throughout the presentation, you can feel free to send Monica a private message and she would be happy to help you with that. And now just a little bit about Watersheds Canada. Watersheds Canada is a nonprofit and charitable organization based in Perth, Ontario. We deliver programs across the country in partnership with landowners, community groups, and students who are looking to take action to protect their fresh water. So you can see some of our different programs in the photos. So on the top left is our nature discovery program. So this is a newer program where we help children and youth connect with nature. And then we also have our Natural Edge program, which was where we work with community groups and shoreline owners to naturalize their property using native plants. And then on the bottom left, you can see our Love Your Lake program, which is delivered in partnership with the Canadian Wildlife Federation. And it's a shoreline evaluation program where we fill out an assessment for each property on a lake, and each property owner gets custom recommendations that are voluntary for their property that can help with protect the health of their lake. And then finally, on the bottom right, we have our fish habitat restoration program. And in this program, we work with community groups to lead projects such as walleye, spawning bed restorations, cold water creek enhancements, and adding woody debris with brush bundle projects. So if you're interested in learning more about our work as a whole, we don't have all of our programs up on the screen, but you can learn about them all at our website, which is watersheds.ca. And the program that we're here for today is the Freshwater Stewardship Community. And through the Freshwater Stewardship Community, it's an online community that helps connect people from across the country. And we're on year 3 of this community, so we're really excited to have you here today. And I just wanted to take a moment to let you know about some interesting things that we have going on. So one of them is our symbolic adoption. So now that the snow is on the ground, we're getting in that holiday spirit. And if you're looking to give a gift that makes an impact, I would encourage you to check these out. So with each of our symbolic adoptions, it features artwork from a Canadian artist, and the proceed of the symbolic adoption helps protect the habitat of the species that are featured in these photos. So there's just a couple on the screen, but we have a lot more on our website at watersheds.ca/gift. And when you purchase a symbolic adoption, you'd receive a blank honor card, as well as a 5x7 postcard featuring the artwork from the Canadian artist. So that's a great gift for this year if you're still looking. And then on to the next slide. We still have some time to give a donation for this year. Before the end of the year, if you give a donation, you'll receive a 2023 tax receipt. We really appreciate any amount that you're able to give. We're a nonprofit and Canadian charity, so we rely on the financial support of people like you to help us increase the knowledge about freshwater stewardship in Canada. And now just a little bit more about the freshwater stewardship community before we get started. So we're on year 3 of this program, and we have lots of resources archived that you can find on our website. So right now we have 42 webinars and 37 handouts with lots of educational content, all about different freshwater issues from speakers that were in academia, other nonprofits, and some local businesses. So I would encourage you to check those out after today. And I'd also just like to thank our funders for the freshwater stewardship community this year, the ECHO Foundation, the SM Blair Family Foundation, and the KM Hunter Charitable Foundation. And so here's an example of one of the handouts that we've sent out from a past webinar. So after the presentation today, you can expect to receive an email with the recording of the webinar, as well as some information about the key points from the webinar and resources that you can use to take action after today. So I'd encourage you to take a look at that once it comes across later in the week. And now a little bit about our speaker today. Liz Favot is an aquatic scientist in Sudbury, Ontario, who has worked for the provincial and federal government in various roles over the last 3 years, ranging from helping to coordinate a compliance assessment. Liz received her PhD from Queen's University in 2021. Her research utilized paleolimnology to reconstruct multi-century trends in nutrients, oxygen, and primary production, and investigate the environmental triggers for recent cyanobacterial blooms in oligotrophic and minimally disturbed lakes. In her spare time, Liz serves to represent Eastern Canada on the board of directors of the North America Lake Management Society. So with that, I will pass it over to you, Liz.
Thanks so much, Nicole. I unplugged my second screen, so I'll see if this works better. But we might have to revert to the old way. So, okay, no, sorry.
It looks good on our end.
Yeah. 1 second. All right, let's go here. One sec. This bar has to go away so I can swap the screens. There we go, finally. Okay, there we go. You see my video, or is the video bar in the way, or is anything in the way, or you're just seeing the slides?
It looks good on our end. You're all good to go.
Perfect. Okay. Yeah, good afternoon, everyone. Thanks so much for inviting me to share my research with you today. My presentation is going to be a summary of my PhD and doctoral research, which was completed in affiliation with Queen's University. And it's going to focus on the memory of the mud at the bottom of lakes and how paleolimnology can help to investigate the environmental drivers of cyanobacterial blooms. Okay, so the only thing is that advancing the slides isn't working. 1 sec. There we go. So to start off, although the term blue-green algae is commonly used to describe cyanobacteria, that's actually a misnomer. The term blue-green algae is misleading because cyanobacteria are fundamentally different at the cellular level from other true forms of algae like diatoms and green algae. Instead of being algae, cyanobacteria are actually photosynthetic bacteria. So you're going to hear me say cyanobacteria a lot, but they're the same thing as blue-green algae. Cyanobacteria is just a better name for them. So cyanobacteria are one of the oldest organisms on the planet. They evolved about 3 billion years ago, and they actually played a critical role in the evolution of nature as we know it, because they were responsible for the great oxidation event of our atmosphere. And because they have such a long evolutionary history, cyanobacteria are well adapted to many different conditions. And so you can find them in most illuminated environments on Earth, everywhere from in the snow of glaciers at the poles to hot springs, to symbioses with fungi and lichens on rocks. And of course, they're also a very common component of our ocean and freshwater phytoplankton communities. There's over 2,700 named species of cyanobacteria, and the group probably contains several thousands more that we've not discovered yet. And cyanobacteria have diverse forms, from a unicellular lifestyle, like these picocyanobacteria, to colonial or groups of cells, like microcystis, to filamentous forms, like dolichospermum. And these filamentous forms have specialized cells to perform different functions for the organism, like nutrient acquisition and for surviving adverse environmental conditions. And actually, the size difference from the smallest cyanobacteria cells up to the largest colonies is like the difference between a flake of ground cayenne pepper and a soccer ball. And this, such a large size difference, has important ecological implications, because these larger forms, like microcystis colonies, are much less likely to be eaten by zooplankton. And the main point of this slide is that there's a lot of diversity in cyanobacteria, and there's several thousands of species, but there's actually only a handful that form blooms in freshwater. And that's like these species shown here that we're going to focus on today. So what exactly is a cyanobacterial bloom? Well, there's actually no strict scientific definition, but it generally describes a dense accumulation of cells that become visible to the human eye. So it's when one or a few species come to dominate the algal community in a water body. And I say there's no strict scientific definition because blooms can be measured in different ways by scientists. So for instance, we can define a bloom based on the total number of cells per liter of water, or we could base it on the proportion of a whole algal community that's made up of by a certain species, or we can base whether or not there's a bloom on the concentration of photosynthetic pigments like chlorophyll in the water. Cyanobacterial blooms are on the rise worldwide, and they've been detected in more and more water bodies over the last few decades. And this slide shows some news clippings of cyanobacteria in Canadian lakes that have had recent media coverage. Blooms have now been documented in all 5 of the Great Lakes and hundreds of inland lakes in Canada, and they can have severe economic and health impacts. And an example of that comes top of mind is in 2014, toxins from a bloom in Lake Erie caused a 3-day complete water shutdown for over 500,000 people in the city of Toledo, Ohio. And a similar 2-week-long water crisis occurred for the residents of Pelee Island, Ontario, just a few weeks later. But there's many negative consequences of both toxin-producing and non-toxic blooms. So species of cyanobacteria, some of them are capable of producing toxins. And when you have a bloom, even if it's a species that we know is capable of producing toxins, it doesn't always produce toxins under different environmental conditions. So if you have a species present that is a known toxin producer, the only way we know if there's toxins or not is if we test the water for toxins. But so, of course, toxin producing blooms are a health risk to humans and pets and livestock. But both non-toxic and toxin producing blooms decrease water clarity or increase turbidity. And this has consequences in light limitation for other photosynthetic species, and also reduces the aesthetic and economic value of the water body. And all sorts of blooms reduce bottom water oxygen, which can result in reduced suitable habitat for certain fish that require high oxygen environments, and also exacerbate a process that we call internal nutrient loading, which I'm going to describe later. And then this internal nutrient loading can act as a positive feedback cycle to fuel future blooms. The causes of cyanobacterial blooms are pretty complex, but you can categorize them at a high level into these 3 main ingredients that contribute to cyanobacterial blooms. So the first is nutrients, and that includes nutrients that come from both natural and anthropogenic or human-caused sources, and come from both runoff from the catchment of the lake, as well as from the process of internal loading, or nutrients that come from within the lake itself. And the cyanobacteria that I'm going to be focusing on today that often form blooms in fresh water, such as Dolichospermum, Aphanizomenon, and Gliotrichia, these are species that have the unique ability to fix atmospheric nitrogen and make it into a form that's usable for them. So they're actually not dependent on the concentrations of nitrogen within the water. And so really the nutrient that usually limits blue-green algal bloom growth is phosphorus. And so that's a nutrient that we're going to be focusing on, especially today. In addition to elevated nutrients, another ingredient that can promote cyanobacterial blooms is specific weather conditions like elevated temperature and stagnant conditions or reduced wind. And then the third ingredient is top-down control or changes in grazing or predation on the algal community. And then we have climate change that alters conditions across all of these categories to make conditions more favorable for blooms to occur. So it can kind of be thought of as a threat multiplier in the case of conditions that promote cyanobacterial blooms. So just to switch gears a little bit here, before I describe some of the main ways that climate warming is bolstering cyanobacterial blooms, we need to understand the process of thermal stratification in lakes. And this might be old hat to a lot of you, but just in case it's new to some people, I'd like to go over it really quickly. So in most moderately deep temperate lakes in Canada, so not Arctic lakes, but in the temperate zone, in the spring, after the ice melts off the lake, the water is cool and of a uniform temperature, somewhere around 4 degrees Celsius. And so all of the water of the lake mixes together and oxygen and nutrients are distributed throughout the water column. But then throughout the summer, as the surface waters of the lake start to heat up, this creates layers of water of different temperature and therefore different density. And if this thermal gradient or this change in temperature becomes steep enough or pronounced enough, then the layers of water will be such different densities that they'll stop mixing with each other. And this is why if you jump into a deep lake near the end of summer, if you reach down deep enough with your feet, you might hit a layer of much colder underlying water. And we call this layering of water of different temperatures through the summer thermal stratification. And during stratified conditions, when we have this layering of water of different temperatures, the hypolimnion or the cold, dense bottom waters are isolated from atmospheric oxygen. So the oxygen that's in this layer, once this thermal stratification sets up, is slowly depleted throughout the summer as organisms that live here consume it. And when oxygen is depleted from the bottom waters, phosphorus that's normally bound to iron in the sediments under oxygenated conditions becomes mobile and is released into the overlying waters. And this is a process that we call internal nutrient loading. So it's been widely hypothesized that climate change will result in more frequent, severe, and widespread cyanobacterial blooms on a global scale. And this is because cyanobacteria possess certain adaptations that allow them to thrive and outcompete other algae groups under the conditions that are posed by climate change. So specifically, in moderately deep temperate lakes, recent climate warming is resulting in a longer period and stronger periods of thermal stratification in lakes, this layering of water of different temperatures that develops in the summer, as well as a longer ice-free growing season. And bloom-forming cyanobacteria do well under these climatic conditions, firstly because they generally reach their maximal growth rates at elevated water temperatures, but also these taxa possess gas vesicles, and this is very unique to certain bloom-forming species of cyanobacteria. Other algae groups don't have these gas vesicles, and this allows them to control their buoyancy or control their vertical position within the water column. And that means that unlike other algae groups, they're not at the mercy of turbulence, mixing, and currents within lakes to remain in an area with adequate light to photosynthesize. So they can continuously thrive under stagnant conditions. This buoyancy control also allows them to monopolize the light area of the lake and shade out other photosynthesizers. And again, very importantly and very unique to these bloom-forming species of cyanobacteria, it actually allows them to move down in the water column and access hypolimnetic nutrient pools that form through internal loading from the sediments when bottom waters are oxygen depleted. And so because of these physiological features, cyanobacteria dominance is expected more frequently in more lakes under a warming climate. So in my postdoctoral research, I examined how trends in confirmed cyanobacterial bloom reports have varied across time and space in Ontario over the last 25 years. So this data set is based on the fact that in Ontario, the public is encouraged to report suspected algal blooms to the Ministry of the Environment by calling the Spills Action Centre. And when the ministry receives one of these calls, they go out to the affected lake and they take a grab sample that looks like this. And then they analyze it under the microscope. And in cases where cyanobacteria is found to be abundant, like in this case, the incident would be tracked as a confirmed cyanobacterial bloom report. And so over a decade ago in 2011, Winter and colleagues documented a significant increase in the number of these confirmed cyanobacterial bloom reports in Ontario between 1994 to 2009, going from just a couple reports in the late 1990s to over 15 reports per year in the late 2000s. Winter and colleagues also documented that about a quarter of these confirmed bloom reports were coming from oligotrophic or low productivity lakes with spring total phosphorus less than 10 parts per billion or micrograms per liter. And this is important because these are phosphorus conditions. Remember, I said phosphorus is the primary limiting nutrient for cyanobacterial growth. These are conditions where phosphorus is so low that we expect that cyanobacterial blooms should be very rare. But Winter et al. Found that a quarter of reports were coming from these low nutrient lakes. So we found that over the last decade since this finding, there's been a continued and in fact much more pronounced increase in the number of confirmed cyanobacterial bloom reports in Ontario, with over 50 reports per year in the last 3 years of the data set. And we also found a similar increasing trend in the number of water bodies reporting their first instance of a cyanobacterial bloom each year. So that indicates to us a growing number of affected water bodies over time. Then we wanted to look at where these bloom reports are coming from. So the map on the right here just shows how population density is spread across the province of Ontario, and that almost 95% of Ontario's population is clustered around the southern border. So we just have to take this into account when we're also interpreting the reports of confirmed reports of cyanobacterial blooms, which are shown on this map as the blue dots. So naturally, since these bloom reports originate from they're initiated by a public complaint, there's an overlap in the bloom report locations being concentrated where there's a high number of lakes and also a high number of people watching lakes to report blooms. So specifically, we found that 80% of the water bodies with confirmed cyanobacterial bloom reports were in the Georgian Bay and Lake Simcoe-Rideau ecoregions within this red circle. So then next we wanted to look at what that most important nutrient for bloom formation, phosphorus, was like in these affected water bodies. So we took the two ecoregions where bloom reports occurred most frequently, Georgian Bay and Lake Simcoe-Rideau, and we overlapped the bloom reports data set with spring water chemistry data from the Ontario Lake Partner Program, which is a community volunteer-based lake monitoring program that's run by the Ministry of the Environment out of the Dorset Environmental Science Centre. And we did that in order to examine spring total phosphorus concentrations in water bodies with no confirmed bloom incidents, which is shown in teal, 1 or 2 years of confirmed cyanobacterial blooms, which is shown in yellow, and 3 or more years of cyanobacterial blooms, which is shown in red. On the y-axis here is the nutrient concentration, and then the black dot in each of these shapes represents the average. So that's what we were really interested in comparing among groups. These numbers show how many lakes were in each category. And the width of the shape just shows that there were a lot of sample points or water bodies that were within that category. So for example, there in the Georgian Bay ecoregion, there's a very large number of water bodies with no confirmed blooms that have spring total phosphorus in the oligotrophic range, less than 10 micrograms per liter. So what we found from this was that a large proportion, or 44% of lakes that had at least one confirmed cyanobacterial bloom have spring total phosphorus less than 10 micrograms per liter. And that's up from the 26% that was reported a decade ago by Winter and colleagues. So we have more cyanobacterial bloom reports occurring in low nutrient lakes. It's also interesting to note that 84% of water bodies with at least one confirmed cyanobacterial bloom have spring total phosphorus under 20 micrograms per liter, which is our provincial water quality objective. And this objective has been put in place to limit the nuisance growth of cyanobacteria. So it's interesting to note that despite this provincial water quality objective aiming to limit cyanobacterial blooms, we've actually found that the majority of confirmed cyanobacterial blooms have occurred in lakes that that already meet this, already have nutrient concentrations less than 20 micrograms per liter. And then finally, we wanted to see if there were any significant differences among these groups among spring total phosphorus concentrations between lakes with no blooms and lakes with reoccurring blooms. And what we found was that the only significant difference in spring total phosphorus concentrations was within the Georgian Bay ecoregion between lakes with no or 1 or 2 years of blooms and lakes with reoccurring or 3 or more years of blooms. Or to put that another way, we actually didn't find any significant difference in spring total phosphorus concentrations between lakes that had no blooms and lakes that had 1 or 2 years of blooms. So that indicates to us that there's other environmental factors driving cyanobacterial blooms in Ontario in addition to phosphorus concentrations. This graph shows the number of bloom occurrences that were dominated by each of these species, the 3 main species in our data sets from May, and this is when the report came in, from May to December. And then the pattern of the bar indicates the water body type that it came from. And so what we found is that Dolichospermum was the most frequent taxa that occurred across all region and water body types in the confirmed bloom reports. And then the next most frequently dominant taxon was Aphanizomenon in the Ontario Shield ecozone, so in shield lakes, and Microcystis in the Mixedwood Plains ecozone in the far south of Ontario. And Microcystis was especially prevalent, not so much in inland lakes, but in Great Lakes and their abatements. We found that observations of blooms across all taxa were generally most frequent in August and September. Dolichospermum occurred over the longest season, with first blooms reports coming in May, and sometimes the last bloom reports coming in December, whereas if you look at Aphanizomenon, blooms were only reported between July and November. And we found that bloom reports from smaller water bodies like ponds tended to occur earlier in the season, in June or July, whereas blooms in the Great Lakes only started coming in later in the season, starting in August. We also examined the seasonal timing and duration of the confirmed cyanobacterial bloom reporting season. So this line shows the day that the first bloom report came in each year. And then the black line shows the day that the last bloom report came in each year. And the shaded green area represents the length of the bloom reporting period. So to take an example, if you look at this green arrow, this is 2006, and it had both a very early and quite a late last confirmed bloom. And so that was actually the year in our time series that had the longest bloom season, which spanned 224 days between first and last reports of the year. So we wanted to then examine if there was any change that might be happening in the length of this reporting season as a result of climate warming, perhaps making the season longer or shifting the blooms later into the year. So we looked for this in post-2006 data, which is when we had at least 10 bloom reports per year to look at. But we found no significant trend over time in the length of the bloom reporting period becoming longer or shifting in the year. Generally, first bloom reports come in April or May, and the last of the year come anywhere from October to December. So to summarize this data of how confirmed bloom reports have changed in the time and space across Ontario, we found that the confirmed number of reports of cyanobacterial blooms have continued to rise in Ontario over the last decade, and a large proportion are coming from low productivity lakes. We found that the increase in confirmed cyanobacterial bloom reports have occurred in the absence of long-term increases in total phosphorus. And but beyond that, interpreting any drivers of these increasing bloom reports that we saw can't be done, because this data set is based on it's influenced by public awareness and the accessibility of lakes, since the only way a data point makes it into this bloom reporting data set is if it's first seen by a member of the public. So but we still conclude that while the length of the bloom reporting period does not appear to be increasing significantly, we think that it's possible that climate warming and associated changes to lake mixing and thermal properties is contributing to the continued increase in bloom reports that we see in the absence of long-term increases in total phosphorus, and with a high proportion coming from low nutrient lakes. So what we've discussed so far has demonstrated that reports of cyanobacterial blooms are increasing across the province of Ontario, and not just in lakes with well-documented nutrient pollution issues like Lake Erie, but also in undisturbed low nutrient systems like some water bodies in Algonquin Park, for example. But this leaves us with some lingering questions. Firstly, how frequently did cyanobacterial blooms occur in these systems prior to when record keeping began in the 1990s? Did we have cyanobacterial blooms in these lakes in the early 1900s, in the 1800s, or even earlier than that? Or are cyanobacterial blooms a new phenomenon in some lake systems? And then secondly, if cyanobacterial blooms are occurring more frequently in Ontario now than they have in the past, then what are the environmental drivers of this trend? And is climate change playing a role? And answering these questions requires historical context. And since most lakes don't have long-term monitoring records, we turn to the science of paleolimnology to help answer these questions. So paleolimnology comes from the Greek root words paleon, meaning old, and limna, meaning lake. It's the study of lake physical, chemical, and biological conditions over long periods of time. And paleolimnology examines fossil material in lake mud, or more technically sediment, to determine the environmental history of an ecosystem. And how this works is that material from the atmosphere, the catchment, and from within the lake are continuously deposited as sediment to the bottom of the lake. And we take a core of the sediment, which then provides us with a continuous record of environmental conditions in and around the lake from present day at the top of the core, going back centuries or millennia as you move deeper in the mud. And the professor who supervised me liked to say that as you move deeper in the layers of this core, it's like turning the pages of a history book to look further and further back in time. Or basically, the mud keeps a memory of environmental conditions for us. So this allows us to extend the monitoring window for a particular lake, which is typically on the timescale of a couple years, a couple decades if you're really lucky. And that allows us to extend the monitoring window back to hundreds or thousands of years ago to establish the environmental history of the lake, to establish baseline conditions, and to establish what the lake was like prior to any major disturbances of the industrial era. So I like this quote from Rachel Carson. She says, "The sediments are a sort of epic poem of the earth. When we are wise enough, perhaps we can read in them all of past history, for all is written here. In the nature of the materials that compose them and in the arrangement of their successive layers, the sediments reflect all that has happened in the waters above them and on the surrounding lands." So this is by no means an exhaustive list, but these are some examples of the materials that preserve in the sediment that we use to establish a lake's environmental history, and we call them paleoenvironmental indicators. So we have chlorophyll A, which is a photosynthetic pigment present in all photosynthetic organisms, plants, and algae. And so it's useful to infer whole lake primary or algal production or abundance through time. Then we have cyanobacterial actinides, which are the resting cysts of certain cyanobacteria, and they have a thickened cell wall, so they preserve for thousands of years within the sediments at the bottom of the lake, unlike the normal vegetative cells of cyanobacteria. So they can be abundance of cyanobacteria through time. We have diatoms, which are a group of true algae, and they have glass cell walls, so they preserve for thousands of years within the sediments at the bottom of the lake. And we can use them to interpret how nutrient concentrations have changed in a lake, because different species have very different preferences for nutrient concentrations. And we can also use diatoms to examine how climate warming might be impacting a given lake, because the longer and stronger thermal stratification or layering of water of different temperatures that's expected with climate warming should favor slower sinking species when there's less turbulence or more stratification. Then we have chironomids, or non-biting midges. They're a group of flies. If you've been around one of the Great Lakes in May, you've probably encountered these swarms of flies that get in your nose and ears and stuff. And they emerge from the lake in the spring, but their larval stage lives within the sediments of lakes. And they're very sensitive indicators of oxygen near the sediments, because different species have different tolerances for low oxygen conditions. And then lastly, there's the cladocerans. They're an important grazer on the algal community, so shifts in their fossil populations through time can indicate changes in aquatic food webs. So as a case study today, we're going to focus on the memory in the mud of Lake Nipissing. So Lake Nipissing is the third largest lake located entirely within the province of Ontario, but it's relatively shallow for such a large lake. It has an average depth of only 4.5 meters, has a maximum depth of about 7 meters, but that's located in a very small hole close to the outflow of the lake, which is the French River, which runs to Lake Huron. And Lake Nipissing is considered mesotrophic or moderately productive with total phosphorus concentrations on average about 15 micrograms per liter. So to give you the historical context for Lake Nipissing, which will help us to interpret some of the trends that we see in the sediments, archaeological artifacts found on the shorelines of Lake Nipissing indicate that it's been inhabited by indigenous peoples for over 3,000 years. The first Europeans came to Lake Nipissing in the early 1600s, and Lake Nipissing formed an important part of the fur trade route up until the 1800s. The first permanent European settlement came to the Nipissing area just prior to 1880, along with a road and a railway. And this was a period of significant logging and land clearance in the surrounding lands. So this I kind of consider like the first major disturbances or land alteration that occurred around Lake Nipissing. Then in the early 1900s, dams were installed at the outflow of the lake, which raised water level about 5 feet from its former level. And those water levels are maintained to this day, over a century later. In the 1930s, the logging industry was winding down in the midst of the Depression, but the birth of the world's first surviving quintuplets actually brought a tourism boom to the area. It brought 3 million tourists to the shores of Lake Nipissing before the end of the decade. And so that was another source of additional development around the lake. Then in the 50s saw an increase in recreational summer homes and angling on the lake. And through the next couple of decades, Lake Nipissing became among the top 3 most frequented lakes in Ontario for ice fishing. The 1980s saw a startling decline in walleye abundance in the lake. And then finally, we reached the 21st century, which brought the invasion of the spiny water flea and the lake's first documented cyanobacterial blooms, which have occurred in some areas of the lake nearly annually over the last decade. So we're going to use paleolimnology to help us determine from Lake Nipissing sediment records if and when environmental conditions in Lake Nipissing have been conducive to cyanobacterial blooms over the 200 years prior to their first documented appearance in the lake in the 21st century. So to do this, we took sediment cores from 9 sites across Lake Nipissing to adequately assess differences in depth at these sites, as well as differences in shoreline development and differences in wind exposure. And we also chose these sites to correspond with long-term total phosphorus monitoring that the Ministry of the Environment has done since the late 1980s. So generally, Lake Nipissing is what we call polymictic or well mixed. So what that means is that thermal stratification, that layering of water of different temperatures, normally does not develop for long periods of time in Lake Nipissing at most of these sites. And that's because of the shallow depth of these sites and also the extensive exposure to wind. The exceptions to that are Calendar Bay is quite protected, as you can see from the winds of the main lake. And so people have seen thermal stratification develop there, but it does not necessarily sustain itself throughout the whole summer as it would in a deeper lake. And also Campbell's Point has regular summertime thermal stratification because this site is significantly deeper than all of the other sites. There's also differences in the shoreline development around these sites. Most of the sites look like this. They're quite undeveloped. The whole southern shoreline of the lake and much of the northern shoreline is undeveloped. But the North Bay site is quite urban, and Calendar is quite urban as well. And there's moderate agriculture in the west arm of the lake. When we look at total phosphorus concentrations, they have not changed appreciably since monitoring started in the late 1980s. and total phosphorus concentrations are generally between 13 to 16 micrograms per liter at most sites, but slightly higher in Calendar Bay, closer to 20 micrograms per liter. This table shows you the confirmed cyanobacterial bloom reports over time at each of our Lake Nipissing sites. And the main take home here is that Calendar Bay has had the most frequently observed cyanobacterial blooms. They've occurred almost annually over the last decade. Then we have several sites on the lake have never had a reported cyanobacterial bloom. And then we have 3 sites at North Bay, Campbell's Point, and Burritt Island that have had 1 year on record with a confirmed cyanobacterial bloom. So considering all of the sites and comparing a pre-industrial sediment slice from the bottom of the core versus the surface sediments, which represent modern conditions, these are the abundances of these different diatom species that we found in fossils in the core. And the most striking finding was that at all sites, the pre-industrial sediments from 1800 and earlier were dominated by these taxa, while the modern sediments, these taxa disappear completely, and we see dominance by these light, slow-sinking diatoms. So we had a complete turnover in the diatom community over the last couple of centuries. And this specific diatom shift is one that's been documented in many, many lakes in the Northern Hemisphere, including lakes like Lake of the Woods, Lake Superior, and Great Slave Lake. And it's hypothesized that in less turbulent, more highly stratified conditions brought about by climate warming and declines in wind speed, as well as a lengthened open water period, diatoms that can remain suspended in the photic zone for longer periods of time, or ones that are have a high surface area to volume ratio and are smaller, lightly silicified, and sink much more slowly, have a competitive advantage under the conditions imposed by climate warming, where we have lengthened and strengthened thermal stratification. And so, with the exception of Campbell's Point, which, like I said, is so deep that it always has summer thermal stratification, most of these sites are shallow and very exposed to wind and traditionally have not had significant periods of thermal stratification, or that layering of water of different temperatures that occurs when there's low winds and high temperatures. But this shift we're seeing within the paleolimnological record towards these light, slow sinking species indicates to us that across all of Lake Nipissing, we are now seeing the physics and mixing regime change in Lake Nipissing so that periods of thermal stratification at a detailed down core record of diatom communities from Calendar Bay. So that's that location that had the most observed cyanobacterial blooms in our study. And here, sediment depth in centimeters and lead to 10 year is shown on the y-axis. So as you move down the screen, you're getting into older sediments. And then on the x-axis is the abundance of these different species. And what we saw was that the pre-industrial or pre-1880 period, from about 12 centimeters in the core downward, were dominated by these heavy, fast-sinking taxa. Then we move into a distinct period from about 1890 to 1970. And during this time, there was extensive land clearance through logging in the Calendar Bay catchment, as well as a dam built in 1910, which raised water levels by about 5 feet. So this was a period of major land alteration in the catchment. And in this period of time, we see about a 40% decline in these guys, and their replacement, or about a 50% increase in this type of diatom, which likes high nutrients. So this shift suggests to us that nutrients were increasing within Calendar Bay in this time period. Then we move into sediments from the 21st century, from the top 2 centimeters of core, which represents 2000 to 2017. And that's the period where we observed frequent cyanobacterial blooms in the bay. And what we see in this period is a decline in that diatom that likes high nutrients. And instead we see increases in these light, slow sinking, small celled diatom species. So this shift from a pre-disturbance period dominated by these guys to a period coincident with observed blooms dominated by these guys, which occurs around 2000, that's consistent with the bay moving to have longer and stronger periods of thermal stratification than it did in the pre-disturbance period. And just to remind you here, that same enhanced thermal stratification that favors this diatom shift to small slow-sinking species also benefits bloom-forming cyanobacteria because they can regulate their buoyancy to optimize their position in the photic zone. They're not reliant on turbulent mixing, so they can proliferate under stagnant conditions and actually use this to their advantage because they can move down to the hypolimnion and access nutrients that may be internally loaded from the sediment during these periods. So this coincident timing in the sediment record of these small slow sinking diatom species proliferating at the same time as we've seen cyanobacterial blooms, instead of seeing cyanobacterial blooms occur in the bay during this period of nutrient enrichment, highlights the importance of climate-mediated changes to lake thermal structure as an important driver of the observed cyanobacterial blooms. On this graph, we have time running along the x-axis from 1800 to 2020. And I promise this is actually the last overcomplicated graph that I'm going to show today. And the green shaded area on the right-hand side represents the period when cyanobacterial blooms have been observed in Lake Nipissing, and then the darker green lines indicate individual years that had blooms. The horizontal black dashed lines on each of these graphs represent the average from 1800 to 2020. So if you see the trend line rise above that line, conditions are higher than average, and below, conditions are lower than average. The top two graphs display chlorophyll A and cyanobacterial pigments within the sediment cores from these 5 sites across Lake Nipissing. And so what we see is an overall increase in algal and cyanobacterial abundance from about 1930 to modern day at most sites in Lake Nipissing. And then these next 4 plots show climate trends from the closest monitoring station, which is located in North Bay on the northeast shore of Lake Nipissing. And this reveals an accelerated rise in mean annual air temperature since 1980, declining wind speeds, fewer days of ice cover, and increasing precipitation since 1970. This next plot shows diatom inferred phosphorus from Calendar Bay. So how this works is that we take the specific phosphorus optima and tolerance of each individual diatom species that's found within the fossil assemblages at each sediment layer and put them into a model to actually put a number to what total phosphorus concentrations were like 2 centuries into the past. And there's many different ways that we test the validity of these models, but one way is by comparing to direct monitored phosphorus concentrations. And that's shown by, I know it's small, but the gray X symbols on this plot. So we have confidence that the diatoms overlapped well with the measured phosphorus concentrations. And what we see from the diatom inferred phosphorus is a period of nutrient enrichment in Calendar Bay from 1930 to 1990, followed by a period of recovery to present day. And this last graph shows a similar model, but done for chironomid inferred bottom water oxygen. And that shows that the lowest inferred bottom water oxygen occurred over the last decade, coincident with the frequent cyanobacterial blooms that we've seen in Lake Nipissing. So the main takeaway from all of this data is that the increases in inferred algal production, as well as the confirmed observed blooms, have occurred during a time period when nutrients have been relatively stable or maybe even declining in some areas based on both diatom records and direct monitoring done by the Ministry of the Environment since the 1980s. And so while nutrients and especially internal phosphorus loading are playing a really important role in the bloom dynamics in Lake Nipissing, the climatic changes and resulting change to thermal stratification periods and the length of the ice-free season are also very important in triggering recent blooms. And just lastly, these pre-disturbance averages for these parameters from our inferences of paleo indicators can serve as useful So to conclude, the Lake Nipissing sediment records revealed a striking change in diatom communities since the pre-industrial era at 9 sites across the lake. And this specific change indicates lake-wide enhanced thermal stratification due to climate warming, as well as declines in wind speed and a longer ice-free season. The diatom shift that occurred around 2000, as well as reduced chironomid inferred end of summer bottom water oxygen in Calendar Bay, is consistent with the appearance of blooms and also with high frequency buoy measurements of oxygen and stratification that have been done by a group at Nipissing University. And so the climate related physical changes to the water column favors bloom forming cyanobacteria that are able to translocate hypolytic nutrients that form through thermally stratified conditions. And so just to get back to the basics for some main take-home messages here, firstly, cyanobacteria are but blooms or excessive growth of certain species of cyanobacteria can have negative ecosystem level impacts. And unfortunately, with continued climate change, the science suggests that cyanobacterial blooms will become an increasingly common occurrence in our lakes in Ontario and in Canada more broadly. Nutrients, and especially those that come from human activities, and especially phosphorus, are a critically important cause of nuisance cyanobacterial blooms, but they're actually not the whole story. The high proportion of confirmed cyanobacterial blooms in Ontario lakes that have low phosphorus, less than 10 micrograms per liter, as well as reconstructions from our sediment records, suggests that even if nutrients haven't increased in lakes, blooms can still occur in the modern climate. And this is likely because climate warming has several consequences that bolster cyanobacterial blooms, especially through a longer ice-free growing season, warmer surface waters, longer and stronger thermal stratification, and exacerbated internal nutrient loading. For what I can recommend for management, climate change is hard to control. We've been trying to do that for decades. So we need to look at what's in our sphere of influence. And the science in what triggers blooms that I've outlined today is quite complicated. There's often a lot of overlapping factors, but actually the implications of blooms and what we can do to mitigate them is pretty simple. What we can control are immediately are the nutrient inputs. And I did show today that even lakes with no excess nutrients may see climate change induced cyanobacterial blooms. But to minimize that risk as much as possible, we need to keep nutrient concentrations at their natural levels within lakes. And what that specific concentration is for each lake can be determined through paleo studies like those I've shown today, or through long-term monitoring. And one really impactful way to prevent excess nutrient runoff to lakes is by keeping shorelines and watersheds naturally vegetated to intercept and sequester nutrients that flow off the land. There's always going to be ecological surprises since there's so many interacting factors that can lead to blooms. But I do believe that with further research, we're going to be able to pinpoint specific lakes that may be most sensitive to developing climate-induced cyanobacterial blooms. And I think the lakes that may be especially sensitive are ones that have currently have moderate nutrient levels or are classified as mesotrophic, and that are relatively shallow so that low oxygen conditions develop rapidly with stratification, which then causes enhanced internal loading, which really benefits cyanobacterial species. And continuous long-term monitoring of water chemistry as well as temperature and oxygen profiles is absolutely essential if we're going to be able to understand and manage cyanobacterial bloom occurrences into the future. And I'd just like to leave you with why I think paleolimnology is so powerful. And that's that I think that understanding environmental histories of lakes is really the key to putting current water quality issues into context. And establishing baseline conditions in lakes is really critical to inform management targets for important parameters that control blooms, like nutrients and like oxygen. And we need to know what the natural or baseline conditions are like in a given lake in order to know what we're aiming for in restoration. And when monitoring data don't exist, paleolimnology and sediment records are a really useful approach to establish these baseline conditions. And with that, I would just like to sincerely thank you for your interest in attending this webinar today, and thanks so much for listening. And I'm sure we have time for some questions.
Thanks for that excellent presentation, Liz. Just before we jump into the question and answers, I wanted to let you know about our survey. Monica just popped the link in the chat there. If you wouldn't mind taking a moment to fill the survey out, it really helps us understand how you're enjoying the freshwater stewardship community and what topics that you're hoping to hear about in the future. Now I'll start with some of the questions. If you think of any questions, you can feel free to add them to the chat too. So the first question is there any research directed towards determining the triggers for the occurrence of cyanobacteria blooms? Any research directed towards determining the triggers for the occurrence of cyanobacteria blooms is welcome and will be instrumental in guiding both public and government responses. So do you know of any research that we can share that people can read after this?
I could put together, I can't like off the top of my head think of there's so much research going on in this area. And there's so many things that we don't know about the triggers of cyanobacterial blooms. And like, as I think I kind of got into in the presentation, there's so many different environmental factors that can cause cyanobacterial blooms. Like I showed those like 3 main ingredients, like nutrients, weather, and top-down control. So then even under each of those ingredients, there's so many other minor environmental factors like species invasions that can ultimately lead to cyanobacterial blooms. So there's a lot of research going on into the triggers. But I think I would like to take like a couple minutes to put together a list of like where you should turn to first for like really interesting new research in the triggers of cyanobacterial blooms.
Yeah, no problem at all. So what we can do is put together a reading list, and then I will add that into the handout that we'll send around later on, so you can keep an eye out for that in the handout. And the next question is, are there any regulations regarding setbacks and buffer zones for cattle farms adjacent to the lake? If so, how are they enforced?
I don't know. I don't know a lot about farming. I'm lucky that like, not lucky, but most of my lake research has focused on lakes that are that don't have a lot of agriculture on the shorelines, or even in the catchment. They've had some, but it's been pretty limited. They're not agriculturally dense areas. So I'm not sure, but that's a really important question, because nutrient runoff from agriculture is like a very could be a very prominent driver of cyanobacterial blooms.
And do you know where we can get our lake water tested for algae, and do you know the cost?
No, it's mostly like private. It would be, you would need like basically just someone to look under the microscope and see what's there, as if you just want to know is blue-green algae dominant. So anyone, companies with a microscope can do that, but that's usually private consulting companies that do that, and I don't know how much they charge. But this will just be like a quick plug for the Lake Partner program, which would test your lake. It's a citizen science program. I used to work for them as a coordinator, but you can sign up for free, and they'll send a kit to you where you can measure your lake water for phosphorus, calcium, chloride, and they do the analysis for free and post the data publicly at the end of the year. And so that wouldn't tell you what the algae is within your lake, but phosphorus is the most important driver of algal growth. So that's an important parameter to know if people on the call aren't aware of that program already.
Awesome, thanks. We'll definitely link out to that program as well. And I also see in the chat that many lake associations do their own water testing, so you can always check with them to see if they have anyone for that. And now the next question, it says, I am wondering what measures can be taken to reduce the occurrences of algal blooms in our lake. What would be the best or most important thing for us to focus on when communicating to shoreline property owners?
Yeah, it depends so much on context. But you need to know like what your nutrient concentrations in the lake are at right now. What are your or are they normal or are they elevated from what they should be? Are they increasing over time or are they stable? If phosphorus is an issue, keeping shorelines vegetated and the catchment as naturally vegetated as possible will be really important to help prevent more runoff of phosphorus going into the lake. So I really think like prevention and limiting nutrients, keeping them at their natural levels as much as possible is like the most important first step you can do. And then after that, if you're seeing frequent cyanobacterial blooms, there are some more technical lake management solutions for cyanobacteria that I can give you links to read a lot about through the society that I'm on the board of directors for, the North American Lake Management Society. They do a lot of work into not just nutrient control, but actual applied how to get rid of blooms, things like sediment caps to prevent, like just a clay lining to prevent internal phosphorus loading. That's really important to bloom formation. But those kind of like direct preventing blooms from occurring approaches are very rarely applied in Canada because they're expensive. Oftentimes they're a band-aid solution. Like really the most important thing is getting phosphorus inputs under control. And also they don't work very well on lakes that aren't tiny ponds. So it's a difficult question, but there's a lot of research going on, and I could maybe cater the take-home fact sheet to put a couple of those links in there too.
Awesome, thanks. And the next question, if total phosphorus is only measured once in the spring each year, how do you know with certainty that the increase in the number of algae blooms doesn't correlate with increased phosphorus levels over the course of the summer and the fall timeframe?
Yeah, that's a really important question because yeah, obviously like phosphorus concentrations at the time of the bloom would be much more informative to our analysis of what whether blooms are driven by phosphorus concentrations. Unfortunately, like we use spring phosphorus because that's what the Lake Partner Program has. Like that's the most comprehensive data set that we have. But the best measure to correlate with blooms would be both epilumnetic or surface water as well as hypolumnetic phosphorus concentrations just prior to when a bloom appears or while a lake is blooming. And the Lake Partner Program takes phosphorus measurements in the spring and not more often than that, just because of resource limitations. And the spring is typically when lake water phosphorus concentration should be the highest. So you're getting a reading that's kind of conservative and like that's the highest phosphorus should be in the lake technically, except maybe not in the hypolimnian at the peak of summer if there's internal loading going on. But
And how do you tell the difference between diatom inferred phosphorus and anthropogenic phosphorus in sediment cores?
So the diatom inferred phosphorus just tells us what the phosphorus was over time. The sources could have come from human sources, and the only way you would know if it's natural or not is really by just looking at the historical context of that water body, and if you know there was a lot of agricultural development at the time that you're seeing a big peak. To increase in the 1930s up until 1990, and that's when we know there was significant development, land clearance, and settlement occurring in the catchment of Calendar Bay. So it makes sense to us that the diatom inferred phosphorus was stable until that time, and then it started increasing.
And another question here is wondering if you can characterize lakes that are most at risk of developing climate change-induced blooms. And are there any modern technologies or strategies that can prevent the blooms before they happen?
To the second part of the question, not that I'm aware of. I think that would make someone a lot of money if they could figure that out or develop a technology to do that. And I think it just comes back to the fact that like there's no one silver bullet that causes cyanobacterial blooms. There's a lot of interacting factors. There's many different reasons that a bloom can form. Like it's not just nutrients, it's not just internal nutrient loading or changes to stratification or a certain invasive species. It can be all these things interacting at once. But for the first part of the question is like whether we can think of lakes that might be more sensitive. There actually is some, and I'm not really in tune with the research right now because I haven't actually been active in this research for about a year, but I remember a paper coming out about a year ago that was starting to try to classify and identify some water bodies that they think would be most sensitive to having increases in blooms in the future under climate change. So I'll try to find that paper. But based on my understanding, I think it's lakes that are would be especially sensitive to internal develop it easily under climate warming. So lakes that maybe were traditionally polymictic, like Lake Nipissing, because they're shallow and they're wind exposed, but with climate warming, they're going to start to see those periods of thermal stratification where internal loading can start to occur. And then internal loading, it's if you have a lake that's completely remote and has never had development on it, then it won't have a lot of human caused phosphorus in the sediments to release through internal loading necessarily. But if you have a lake that's had a lot of land alteration in the catchment and a lot of phosphorus inputs in the past that are in those sediments but have been bound because the sediments have been well oxygenated, we call it like legacy phosphorus in the sediments. If that phosphorus in the sediment starts to be released because bottom waters become anoxic under enhanced stratification, those would be lakes too that would be pretty susceptible to cyanobacterial blooms induced by climate-related changes to water column thermal properties.
And one last question here. It says, I'm wondering if you have any insights or references for the impact of guano as a trigger for cyanobacteria or others.
I have friends who have done like whole PhDs on this project, like Matt Duda, or Emily Stewart even too. She studied bird ponds on Lake Ontario, where guano was like the main driver of eutrophication. So I'll definitely include some of those references in the fact sheet too. But those are some names if you want to get started. Emily Stewart and Matt Duda.
Perfect. Yeah, we'll make sure to include that. So that will conclude our question and answer period. And thank you so much, Liz, for your presentation. And thank you for everyone for tuning in today. And we're looking forward to have lots of more freshwater stewardship community webinars in the new year. So make sure you stay tuned to our social media and our website for those. And I hope everyone enjoys the rest of your day.
Thanks so much. Thanks, Nicole.